Hello, I'm João, and today I will be talking about our paper called GuiltyWalker, Distance to Illicit Nodes in the Bitcoin Network that was developed in a collaboration between IST and FIDSI Research in 2021. So, money laundering is a high-impact problem on a global scale where criminals obtain money illegally from serious crimes and inject it into the financial system as seemingly legitimate funds. Governments and international organizations are building tighter regulations around money laundering and are broadening them to include cryptocurrencies such as Bitcoin that have become a popular vehicle for criminal activities in the recent years. Thus, it is very important to invest time and efforts in investigating cryptocurrencies and identifying criminal activity. Our work is yet another attempt at helping identifying criminal activity in the Bitcoin network. So with this said, with our research, we aim at describing and answer two questions, being the first, that how can we describe the distance between a given transaction and a known illicit transaction in the Bitcoin network? And the second goal is to assess the impact of such features to detect illicit transactions in the Bitcoin network. With these two questions in mind, we first designed GuiltyWalker, which is a random walker that traverses a given transaction network and describes the distance of certain seed nodes to known illicit nodes. And secondly, we measure the performance of features extracted from the GuiltyWalker in a classification task, where we propose to use a publicly available dataset. So our first and main component in our project is the GuiltyWalker, which consists of two components. The first is the random walker, where given a transaction graph, a set of seed nodes, and the number of desired walks, it samples random walks for each seed node. And the second component is the feature extractor, where given a set of these random walks for each of the seed nodes, it computes aggregated features that summarize these walks. So going deeper into each of these components, the first component is the random walker, which receives as input the transaction graph G, the list of seed nodes S, which is a subset of the vertices of the graph, and the number of successful random walks desired, K. And after defining the inputs, the random walk process is very simple, where starting from a certain seed node S, at the current node, we find the parents of that node. Uniformly at random, we pick one of the parents, P, selected, and the walker travels to that selected parent. And this process is repeated until one of two conditions is met. The first is that the new current node is a known illicit transaction node, and in this case, we will have a successful walk. Or second, the parents of the current node to pick from is empty, and in this case, it is considered an unsuccessful walk. So after this process, the random walker outputs for every seed node S a list of the K successful walks XS, where each XI is a list of the nodes traveled to in that walk. Now, and before proceeding to the next component, I would like to talk about a few considerations in our implementation of the GuiltyWalker, more specifically of the random walker. And the first consideration is that the GuiltyWalker performs as many random walks as needed to ensure the number of desired K successful walks, and that only those are used for feature extraction. The second consideration is that GuiltyWalker first determines which nodes can reach an illicit node, and only these nodes that can reach an illicit node are given as input for the random walker. And the third consideration is something that is derived from the first and the second considerations that are very dataset dependent. And in this case, we have a small network with a short depth. So, but if we extrapolate this work to real world scenarios, there is a scalability problem with our implementation. And in this case, we propose two solutions. The first is to use a maximum walk size, which will put a cap on how deep into the network the random walker is allowed to travel to. And then is the maximum random walks, where instead of performing as many as needed, they will be now fixed and with a maximum number. And the second component of the GuiltyWalker is the feature extractor, where it computes features for each of the transaction nodes and that are listed in this table. The first set of features we named statistic aggregates, and they look to describe the length of these walks, and thus we have the mean and standard deviation of these successful walks. And then we have also the minimum, the maximum, the first quartile, the medium, and the third quartile of the length of the successful walks. And after that, we have features that are not statistic aggregates that seem to describe the walks very well. And the first is the fraction of successful random walks over all the walks performed that we named hit rate. And the second is the number of distinct illicit nodes found that we named illicit. Going further into the details and now more specifically into our experimental setup, and before diving into the results, I would like to talk about the dataset we have used. And we have used the Elliptic dataset, which is the biggest publicly available dataset of labeled Bitcoin transactions released by the Elliptic company in 2019, which maps transaction nodes to real-world entities belonging to one of two categories. The first being illicit category, which describe wallet addresses known to belong to exchanges, wallet providers, miners, and so on. And the second category is the illicit category, where we have wallet addresses known to belong to Ponzi schemes, terrorist organizations, ransomware, and so on. The Elliptic dataset includes around 200K node transactions or transaction nodes, and about that same amount of directed edges describing the flow of Bitcoin between the transactions. Besides that, 21% of the transactions are labeled as licit, 2% as illicit, and the remaining are unknown. And also it is worth mentioning that associated with each transaction node, there is a timestamp. And these timestamps correspond to more or less 2 weeks interval of in time where the snapshot of the network was taken. And there are 49 different time steps, and that each of those correspond to a DAG, and we have a single connecting component inside each. And it means that between time steps, we won't have edges connecting these transaction nodes in different time steps. Besides the graphs, we also have tabular data with 166 anonymized features, where the first 94 are local features describing the amount of the transaction, the number of outgoing edges, incoming edges, and the last 72 features are named aggregated features, and they describe the maximum minimum amount of neighboring transactions. So now that we have cleared what is our data set, I seek to tell you what was the methodology that we have followed. And first, we extracted the GuiltyWalker features after performing 100 successful random walks. Then we performed a 70-30 temporal split of the training test data. And then we obtained the baseline results by training a random forest model using all the 166 features obtained from the original dataset that we now named as WF, standing for Weber features. Before continuing, I would just like to mention that we have actually performed the exact same and followed the exact same methodology as that followed in the original dataset paper, as we are looking to have a full transparency and fairness of the results. So after obtaining the baseline results, we trained this random forest model, which corresponds to the best performing model in the original dataset paper, using only the GuiltyWalker features named GWF, and both the WF and the GWF features. Then, as part of our machine learning stack, we perform permutation feature importance to assess each of the GWF features importance on the training set, and kept the ones with mean importance greater than 0. And after that, we ended up with the features that are in the slide. And we further on trained again the random forest model with both the concatenation of the Weber features and this new subset of the GuiltyWalker features that were kept after feature reduction. Also, it is worth mentioning that in the results to follow, when we are saying GWF, actually what I meant here is these new GuiltyWalker features kept after the feature reduction step. So going into the meteor part and the results, here we have our classification results. And on the left, we have the features where, as I mentioned before, the WF corresponds to the Weber features, GWF to the GuiltyWalker features, and WF plus GWF corresponds to the concatenation of these both sets of features. So in our metrics, we have used the precision, the recall, and the F1 score at the illicit category. And before continuing to the conclusions, I would just like to say that we have, in fact, used the exact same metrics as the ones reported in the original dataset paper, again, for full fairness of the results. So what I want you to take from this graph, from this table, is that the GWF features are not descriptive enough with low recall and F1 score, as you can see, and that the best results are in fact obtained by using both these features with an improvement in the precision and the recall, which enabled us to move the F1 score by 5 percentage points. So continuing further, in this, something that was also explored in the original dataset paper was the illicit F1 score for each of the test time steps. And we performed the exact same study, and in gray we have the number of illicit transactions, and the lines we have the F1 score of the random forest model trained with GWF plus the WF in pink, and the model trained with only the Weber features in red. And something that you can see already from this graph is that at all time steps, the model trained with the GWF plus the WF features also has near or superior performance to the model trained with the original features. And the second result is that after time step 43, which coincides with a black market shutdown, we have a great reduction of the performance of the model trained with WF, where the performance sharply decreases to 0. And in this case, you can see that the model trained with the GWF plus WF features actually has a performance much higher than the ones from the original data, compared to the model trained with the original features. And finally, to conclude our presentation, I would like to talk about the 3 takeaway points from our paper. And the first is that given a transaction network, we propose a method called GuiltyWalker that extracts information from the structure of the network and the existence of past labels to create new features to be used in a supervised model. Secondly, we look to combine these new features with the features proposed in the original dataset and observe an improvement of about 5 percentage points in the illicit classification task. And the third and last is that the performance is actually accentuated after an emerging event, which in this case is a black market shutdown, where the baseline actually performed very poorly. Thank you.